Hi everyone, in this video we're going to talk about Laplace transforms. And when you get to this section of your calculus course or differential equations course, first it seems very intimidating and it's a little bit confusing. What are we actually doing? So I'd like to make it really clear, and it's really they're kind of fun once you get the hang of them. So the analogy I'm going to give you is that of a bicycle. And we've all had bicycles, and when you get a problem with the tire, okay, so maybe there's some problem with your tire, you might be able to just pump it up with air and you go on your way. And that's like, our garden variety differential equation. We see it, maybe we can separate the variables and we go on our merry little way. But sometimes you have got a really big problem, a really nasty tire or a really nasty differential equation. You can't solve it with other methods, with easier methods. They don't work. So what you need to do with your bicycle is you take your tire off and you put it over here, maybe on some sort of workbench. Yeah. And you put your tire over here. And you take the rubber tire off the rim and you work on it and you fix it up quite nicely. And then you go back to your original space, the bicycle, and you put your tire on and you're all set. And working with these Laplace transforms is the same idea. We've got some nasty equation. We're going to transform it to a different space, which is like the table, like in our workshop. We'll work on it. We'll solve it. We'll fix it up. And then we'll just put it back into the original variable. All right. So it's the idea that we're going to take and we're going to work on this equation in some other space, and then we'll come back and put it all together. So how do you transform these equations? Well, in most textbooks, or if you go on a Google search, you will find a table of Laplace transforms. So I'm over here in a textbook. This is called the table of Laplace transforms. Now you can go to other places, as I said, Google and so forth. And so what you've got in this table here, I'll just scroll around a little bit. So the first column here has the function. And then if you want to transform it, this is what you need to write down. All right. So this is like your tire on the bicycle. And then this is how it would look in the transform space if you took that tire and worked on it on your workbench. All right. So I'm going to use this table extensively as I solve this problem. So let's go back. I've got a second derivative, z prime plus omega squared, and that's just some number. It might be 5, might be 2 pi over 10. I don't care. It's just a number. I'm going to keep it there for now. Times z equals 0. So the first thing I need to transform is the second derivative z squared. So what I'm going to do is I'm going to take the Laplace transform of the second derivative of z. And I'm going to write it in square brackets. It's not the function of, but it's just this transformation. So I'm going to write it with the square brackets. So I'll do that for the first term. And by the linearity property of Laplace transforms, I'm just going to go through, and now I'm going to do it to the second term. I'm going to take the Laplace transform of everybody. Nothing tricky. And the Laplace transform on the right of 0 is just going to be 0. You could write it down if you really wanted to. And so really what I've got to do now, my homework is to figure out what is the Laplace transform of the second derivative. Now I can pull this constant out in front, this omega squared, so that'll be a little bit easier to work with. I've just got the Laplace transform of z. And on the right-hand side, the Laplace transform of 0 is 0. So let's go work on this. The first thing I need to do here is figure out what is the Laplace transform of the second derivative of z. So I'm going to go shopping for Laplace transforms. I'm here in my table and I'm looking around. Where is my second derivative? Right here. Okay, f double prime. I've got a z double prime. I don't care. Apples, bananas, what's the same difference? And here's what I need. Okay, so if I transform the second derivative, I'm going to have s squared. This is just your transformation. You're in this other variable. You're on your workshop table working on the tire of your bicycle. We're now talking about the variable z or s. sorry, not z. So we've got s squared, f of s minus s times f of 0, or in our case, z of 0 minus f prime. Okay, that's what we need. Let's go back and write that down in the context of our problem. So the first thing I need is s squared. Okay, so to apply the Laplace transform, I'm going to have, for this first piece right here, I'm going to have s squared times the Laplace transform of s minus s times my initial value. So z, I'm going to call it z naught, or z of 0, minus the first derivative at time equals 0. And that's it. Next, I need to move on to the second term. So I had an omega squared. I'll write that down. Times the Laplace transform of z. So that'll give me L of s. Now, I think if you're working on the discussion problem, they said when you're in the variable z, you should call your Laplace transform capital Z. So I will follow suit with the notation there, and I'll just call this capital Z, not L. I want to write L, so I'm very used to writing L. But they wanted us to use the capital Z for the Laplace transform. So we can do that. That's no problem. And on the right-hand side here, we still had our 0. Okay, the next thing I need to do is I'm going to collect all of the terms with capital Z. The Laplace transform terms, I'm going to keep all of those terms on the left, and I'll move everybody else over to the right. So on the left side of my equation, I'll have a s squared times capital Z, the Laplace transform. And I've got an omega squared, capital Z of s, and then everybody else I'll move to the right side of the equal sign, so I'll have a s times z naught, and I'll have a plus z naught prime. Next, I'm going to pull out a common factor. I've got a common factor of capital Z of s, so I'm going to pull that out, and I've got a s squared plus omega squared times capital Z of s on the left. And on the right-hand side, I still have z naught times s plus z naught prime. In other words, the first derivative evaluated at the initial condition there at time equals 0. Next, I'm going to divide both sides, because ultimately I'm trying to solve for this Laplace transform. I want to know what is capital Z of s, so I'm going to divide both sides by s squared plus omega squared. Goodbye, goodbye. So what we have left, let me just put a little divider here on our screen. What we have on the left-hand side, we have capital Z of s. And on the right-hand side, I have, in the first term, s times z naught over s squared plus omega squared. And in the second term, I have z naught prime over s squared plus omega squared. Okay, let's pause here. Now, this is where I'm at. I'm over here on my workshop table. I'm in the Laplace land, if you want to call it that. I'm in this capital Z of s altered reality, right? I'm working on the bicycle tire on the workshop table, and that's fine. I did solve for that, so I've made a lot of progress, but I need to now put it back on the bicycle. I need to go from this capital Z world back to little z of t. All right, so little z of t, like our goal was to figure out what is z. We had information about the derivative, we had differential equation, and I've made a lot of progress over here on the workshop bench, but now I need to transform, I need to do the inverse transform to get back. So we've done the Laplace transform here, and now we need to invert that process. We need to do the inverse transform to get back and put everything together. So I'm going to go back to my table. Okay, so now I'm in the transformed world and I want to go back to the function. So I need to hunt around in this table to find something that looks like my problem. If I go back to what I have, I've got some sort of fraction, and in the denominator, I've got two variables that are being squared. In my case, I've got an s squared and an omega squared. So I'm hunting around in this table looking for fractions. So I'm over here on the right-hand side of this table. And in my denominator of the fraction, I've got two variables squared. Ooh, definitely not these ones because these have the difference of two perfect squares. That's not where I'm at. And then, other things farther down, also not the form I have. So I really think I'm going to be using something like this cosine or this sine. So let's look carefully here. The first one here says if your transform looks like s over s squared plus some other variable, omega or k squared, whatever, then if you want to go back, if you want to do the inverse transform, your function would be cosine of kt. So let's see if I can make my problem look like that. And in this first term, yeah, I do have an s up there. I just need to pull this z naught out in front. And that's some number. It's your initial condition for z. So it's just some number. It might be 5, might be 10, whatever it is. So let's rewrite this. So z s equals, I'm going to pull my z naught out in front. And then I'm left with s over s squared plus omega squared. And that definitely looks like that cosine function. Now, for the other term here, again, that z naught prime, I could pull that out in front, and then I'm left with this fraction 1 over s squared plus omega squared. And going back to my table, I don't have that. I do have something for sine if I can get a k, or in my case, an omega up in that numerator. So to do that, I'm going to multiply by omega over omega. Let me make that clearer. Okay, so now we're ready to roll. I'm going to apply the inverse transform. So this is going to be the inverse transform applied to z of s. On the right-hand side, the inverse transform of everything here, plus the inverse transform of z naught prime over omega times omega over s squared plus omega squared. So the inverse transform of the transform is just the original variable, which is z of t. Haha, we have made it back to our bicycle. We've made it back to our original variable, z of t. And then on the right side, the constant pulls out in front, which is z naught. And the inverse transform of s over s squared plus omega squared, that is going to be cosine of omega times t. And the other one is a sine of t. And I'm done.